Hello and welcome. I am so glad you chose to be here tonight. Wherever you are right now, whatever kind of day this was, whether it was long or short, heavy or light, you have arrived at the end of it. You made it through. And now this time is yours. This quiet, this darkness, this moment of finally letting everything go. Tonight we are going to a world that has captured the human imagination more deeply than perhaps any other world in the solar system. A world we have been watching, studying, and dreaming about for centuries. A world of extraordinary geological drama, of ancient canyons and colossal mountains and dry riverbeds that still remember water that stopped flowing billions of years ago. A world where right now, at this very moment, robotic rovers are driving slowly across a dusty orange landscape, examining rocks and taking photographs, and sending everything home to scientists who spend their days piecing together the story of a world that used to be very different from what it is today. Tonight, we go to Mars, the real Mars, the geological Mars, the Mars of actual rocks and actual craters and actual volcanoes and actual canyons, the Mars that formed 4.5 billion years ago alongside the rest of our solar system, the Mars that was once warm and wet and in some ways not entirely unlike a younger version of Earth, and the Mars it became, the cold and quiet and beautiful red world that our spacecraft now explore. Everything I am going to tell you tonight is true. Every measurement, every discovery, every story, it all happened. It is all real, and by the time we are done, you will understand this world in a way that will make it feel less like a faraway planet and more like a place you have actually visited, a place you know, a place that feels familiar in the quiet and beautiful way that all truly remarkable places feel familiar once you have spent enough time with them. Before we begin, take a long, slow breath in, fill your lungs all the way, hold it for just a moment, and breathe out slowly, letting your whole body soften with the exhale. Feel where you are lying, feel the warmth of your blanket, feel your shoulders drop, feel the tension in your face release. You are safe, you are warm, you are exactly where you need to be, and we are going somewhere extraordinary together. Let your eyes stay closed. Let the world outside this room fade away, and let us travel to the fourth planet from the Sun. Mars orbits the Sun at an average distance of about 228 million kilometers. This is roughly 1.5 times the distance from Earth to the Sun. At its closest approach to Earth, Mars comes within about 56 million kilometers of us. At its farthest, when the two planets are on opposite sides of the Sun, it is more than 400 million kilometers away. The average distance between Earth and Mars is around 225 million kilometers, and at the speed of light, a radio signal takes about 12.5 minutes on average to cross that distance when NASA's engineers send a command to one of the rovers on Mars. They wait 12 minutes or more for confirmation that it arrived. A conversation in slow motion stretched across hundreds of millions of kilometers of space. A day on Mars is remarkably similar in length to a day on Earth. A Martian day, called a sol, lasts 24 hours and 37 minutes. This is only slightly longer than our own 24-hour day. If you were standing on the surface of Mars, the sun would rise and set, and the stars would appear at night on almost the same cycle you experience on Earth. This similarity in day length has always struck people as curiously comfortable, as if Mars was trying to say that it is not entirely alien, that it operates on a rhythm at least somewhat familiar to us. A year on Mars, however, is nearly twice as long as an Earth year. Mars takes about 687 Earth days to complete one orbit around the Sun. This means the seasons on Mars are about twice as long as they are on Earth. A Martian spring lasts roughly 170 Earth days. A Martian winter lasts just as long. Mars is also tilted on its axis at about 25 degrees, very similar to Earth's 23. 5-degree tilt, which means it experiences seasons in the same general way we do. Northern Hemisphere winter, when the North Pole tilts away from the Sun. Northern Hemisphere summer, when it tilts toward it. If you were standing on Mars, you would feel the seasons change over the long Martian year, though the temperature changes they bring are extreme by Earth standards. The average temperature on Mars is about minus 60 degrees Celsius, but this average masks an extraordinary range. At the equator, on a summer afternoon, the temperature can reach a relatively mild 20 degrees Celsius, similar to a cool spring day on Earth. In that same location, after the sun sets and the thin atmosphere releases its heat rapidly into space, the temperature can plummet to minus 80 degrees Celsius before morning, and at the poles in winter, temperatures drop to around minus 125 degrees Celsius, cold enough for carbon dioxide from the atmosphere to freeze out of the air and form a thin layer of dry ice on the polar surface. The atmosphere of Mars is thin, very thin. The atmospheric pressure on the Martian surface is less than 1% of the atmospheric pressure on Earth's surface. The atmosphere is composed mostly of carbon dioxide, about 95%, with small amounts of nitrogen and argon and trace amounts of other gases. There is almost no oxygen. You could not breathe on Mars without a pressurized suit and an oxygen supply. And the thin atmosphere provides very little protection from radiation from space, which reaches the Martian surface at levels that would be harmful to an unprotected human over time. The atmosphere also provides very little insulation, which is why the temperature swings so dramatically between day and night. Mars is smaller than Earth. Its diameter is about 6,779 kilometers compared to Earth's 12,742 kilometers. Mars is roughly half the size of Earth. Its surface gravity is only about 38% of Earth's surface gravity. If you weighed 70 kilograms on Earth, you would weigh only about 26.5 kilograms on Mars. You could jump roughly 2.5 times as high as you can jump on Earth. The lower gravity has profound consequences for the geology of Mars, as we will see. And now let us talk about the color. The most immediately striking thing about Mars, the thing that has defined its identity and earned it the name the Red Planet, is its color. From Earth, even with the naked eye, Mars glows with a distinctly reddish-orange light. Early civilizations across the world noticed this color and associated it with fire and blood and war. The ancient Romans named the planet after their god of war, Mars. The ancient Greeks called it Ares, their own god of war. In many other cultures around the world, the red wandering star in the night sky was associated with conflict and power and aggression, all because of a color, all because of chemistry. The surface of Mars is covered in iron oxide, rust, the same compound that forms when iron is exposed to oxygen and moisture and turns the brownish-red color we see on old nails and old bridges and old machinery. Billions of years ago, when Mars had liquid water and a thicker atmosphere, the iron in the rocks and soil of Mars reacted with oxygen and water and formed iron oxide. As Mars dried out and its atmosphere thinned over billions of years, the liquid water disappeared. But the rust remained. It was ground up by wind and meteor impacts into a fine dust, and that dust covered everything: the rocks, the soil, the cliffs and craters and mountains, all of it coated in this ancient rust. The dust is so fine and so pervasive that it is suspended in the Martian atmosphere, giving the sky a distinctly pinkish tan color by day. Not the blue of Earth's sky, but a muted butterscotch orange. At sunrise and sunset, the sky near the sun turns a pale blue, the exact opposite of Earth, where sunsets are red. On Mars, sunsets are blue, and the rest of the sky is orange. It is a beautiful inversion, a reminder that you are on a world where many things are familiar, but nothing is quite the same. The Martian soil is often described as regolith, a general term for the loose, unconsolidated material covering the surface of a rocky body. Martian regolith is a mixture of this iron oxide dust with rock fragments and minerals. It is not a good growing medium. It is dry and poor in nutrients and contains compounds called perchlorates that would be toxic to most earth plants without treatment. But it is the result of billions of years of geological processes, of volcanic eruptions and asteroid impacts, and the action of ancient water and the grinding of wind. It is, in its own way, a record of the history of Mars, written in chemistry and grain size and mineral composition. And speaking of geological processes, let us now travel to the most dramatic geological features on the surface of Mars. Because Mars is a world of superlatives when it comes to geology, it holds records that nothing else in the solar system can match. Let us go first to the northwest of Mars, to a region called the Tharsis Plateau. This is a vast elevated area on the surface of Mars, a bulge of elevated terrain roughly the size of North America, rising several kilometers above the surrounding plains. The Tharsis Plateau is the result of billions of years of volcanic activity, enormous outpourings of lava from deep within the Martian interior that built up this vast elevated region over geological time. It is one of the largest volcanic features in the entire solar system. On top of and around this plateau sit some of the largest volcanoes in the solar system. The Tharsis region contains 3 enormous shield volcanoes aligned in a diagonal row called Martian Mons, Phobos Mons, and Ascraeus Mons. Each of these volcanoes is itself a remarkable structure, larger than any volcano on Earth, but they are merely the supporting cast to the most extraordinary geological feature on the surface of Mars: Olympus Mons. Olympus Mons is the largest volcano in the solar system, the largest mountain of any kind in the solar system, measured from base to summit. Its summit reaches approximately 21.9 kilometers above the Martian datum, the Martian equivalent of sea level. To put this in perspective, Mount Everest, the tallest mountain on Earth measured from sea level, reaches 8.85 kilometers. Olympus Mons is nearly 2.5 times taller than Everest. If you stood at its base, you would not be able to see its summit. The mountain is so wide, roughly 600 kilometers across at its base, that the curvature of Mars would hide the summit below the horizon. You would have to be far enough away from the mountain to see its full height, and from that distance, it would still dominate the sky. The reason Olympus Mons grew so large is directly related to Mars's geology. On Earth, the crust is broken into tectonic plates that move slowly across the surface. This movement carries volcanic hotspots from place to place. A hotspot under Hawaii, for example, has been building volcanic islands for tens of millions of years. But as the Pacific Plate moves, the islands that form are carried away from the hotspot, and new ones form in its place. This creates the chain of Hawaiian islands, each one older than the next, as you move northwest from the Big Island. The volcanic activity is spread out across many mountains because the plate keeps moving. Mars does not appear to have active plate tectonics in the same way Earth does. The Martian crust is largely a single rigid shell. Hotspots in the mantle below the crust stay fixed relative to the surface above. The magma keeps coming up through the same place, decade after decade, century after century, million year after million year. The same location receives lava continuously for an almost incomprehensibly long time, and the result is a single mountain that keeps growing and growing and growing until it becomes something the size of Olympus Mons. The summit of Olympus Mons is a massive depression called a caldera, a collapse feature that forms when magma drains out of the chamber beneath a volcano and the roof collapses inward. The caldera at the summit of Olympus Mons is about 80 kilometers across and 3 kilometers deep, large enough to contain a small country. The flanks of the mountain slope very gently, like a shield lying face down, which is why this type of volcano is called a shield volcano. The slope is so gradual that if you were walking across the flanks of Olympus Mons, you might not even realize you were on a mountain. You would just be walking across a very slowly inclining plane. At the outer edge of Olympus Mons, the terrain changes abruptly. A cliff called the escarpment rings the entire mountain, in some places rising as high as 8 kilometers vertically. Standing at the base of this cliff and looking up would be a view unlike anything available anywhere on Earth. A wall of volcanic rock rising to a height that would dwarf the tallest cliffs on our planet, and above that cliff, the vast, gently sloping shield of the largest mountain in the solar system, extending 300 kilometers to the summit. Scientists believe Olympus Mons may have last erupted as recently as 25 million years ago, which makes it geologically young. Some scientists speculate that it may even still be volcanically active, capable of erupting again in the future, though we have no direct evidence of a recent eruption. If it did erupt, the lava flows would be extraordinary events, pouring down the flanks of the mountain and rivers of molten rock that could travel hundreds of kilometers. Now let us travel to the most dramatic canyon in the solar system. From the Tharsis Plateau, we move eastward, and almost immediately we encounter a geological feature of staggering scale. The beginning of Valles Marineris. Valles Marineris is a system of canyons stretching along the Martian equator for a distance of about 4,000 kilometers. For comparison, the Grand Canyon in Arizona, one of the most famous geological features on Earth, is about 446 kilometers long and up to 1.6 kilometers deep. Valles Marineris is nearly 10 times as long as the Grand Canyon. In places, the canyon reaches depths of up to 7 kilometers. In its widest sections, it stretches 200 kilometers from wall to wall. If Valles Marineris existed on Earth, it would stretch from Los Angeles to New York with room to spare. The canyon system is not the result of a single river cutting through rock the way the Grand Canyon formed. The origin of Valles Marineris is related to the Tharsis Plateau nearby. When the enormous volcanic mass of Tharsis bulged upward from the Martian crust, the enormous weight and the internal pressure created fractures in the surrounding crust. These fractures radiated outward from the Tharsis region, and over time they widened as the walls of the fractures eroded and collapsed. Water may also have played a role in widening and deepening the canyon system in ancient times, when Mars had liquid water flowing on its surface. What began as tension fractures became, over billions of years, a canyon system of incomprehensible scale. Standing at the rim of Valles Marineris and looking down would be an experience of vertigo unlike anything on Earth. The floor of the canyon would be almost 7 kilometers below you, twice the depth at which commercial aircraft cruise. The opposite wall would be 200 kilometers away, beyond the horizon. The floor of the canyon would be filled with landslide debris. Huge masses of rock that have broken from the walls over billions of years and piled up on the valley floor. Ancient dried streams cross the floor. Layered rock in the walls tells the story of billions of years of geological history, layer by layer, each one a chapter in the long story of Mars. Within the canyon system there are regions of extraordinary complexity, chasmata, broad valley sections, labyrinthous terrains, areas of intersecting valleys and mesas that look almost like the ruins of some vast geometric city, mons and plateaus that rise from the canyon floor, enormous landslides frozen in geological time, their debris fans spreading out across the floor exactly where they fell, perhaps hundreds of millions of years ago, with nothing to erode them or move them since. The walls of Valles Marineris are among the best natural geological records on Mars. The layers of rock exposed in those walls represent billions of years of deposition, volcanic activity, and the action of water. Scientists studying images from orbiting spacecraft have identified dozens of distinct rock layers in the canyon walls, each one representing a different era in Martian history. Reading those layers is like reading the pages of a very ancient book, a book written in minerals and rock and dust over billions of years. Let your breathing slow a little more. You are drifting beautifully. Let the images of Mars settle gently behind your closed eyes. The red landscape, the towering walls of ancient canyon, the vast flat summit of Olympus Mons touched by thin cold sunlight. Let it all be peaceful. Let it carry you deeper. Now let us talk about the most important thing we know about Mars, something that changes everything about how we understand this world. Mars was not always the cold, dry, thin atmosphere desert it is today. Once, billions of years ago, Mars was a very different world. Approximately 4 billion years ago, during the era that geologists call the Noachian period, Mars may have had a warmer and wetter climate. The evidence for this is written all over the surface of Mars in features that can only be explained by the action of liquid water. River valleys. Deltas, ancient lake beds, mineral deposits that form only in the presence of water. All of these features, seen in images from orbiting spacecraft and studied up close by rovers on the surface, tell the same story. Water flowed on Mars, perhaps a lot of water, for a very long time. The ancient river valleys of Mars are called valley networks, and they are found predominantly in the southern highlands, the older and more heavily cratered terrain of the southern hemisphere. These are branching systems of valleys that look remarkably like river drainage systems on Earth. They have tributary systems that feed into larger main channels, exactly the way rivers on Earth have small streams that feed into larger rivers. The branching pattern of these valley networks suggests they were carved by precipitation, by rain or snowmelt flowing down slopes and collecting in valleys, in the same way that Earth's river systems are fed by rainfall. Some of these ancient valleys are enormous. The Gale Valles system, one of the largest outflow channels on Mars, is more than 3,000 kilometers long and in places more than 300 kilometers wide. Features like this were not carved by slow river erosion over time. They were carved by sudden, catastrophic floods. At some point in Mars's history, enormous amounts of water were released very suddenly, perhaps from the melting of underground ice caused by volcanic activity or by a large impact. The water flooded across the surface in quantities that dwarf any flood in recorded human history. It carved enormous channels in hours or days before freezing and sublimating away. The dry channels remain as evidence of these ancient catastrophes. The minerals found on Mars also tell the story of water. The Mars Reconnaissance Orbiter and other spacecraft have detected clay minerals, also called phyllosilicates, in many ancient terrains on Mars. Clay minerals form in the presence of liquid water. They are the product of water interacting with volcanic rock over extended periods of time, breaking down the rock chemically and creating new mineral compounds. Wherever clay minerals are found on Mars, scientists know that liquid water was present for long enough to alter the rock. In some locations, clays have been found that would have required continuous water exposure for millions of years to form. Sulfate minerals have also been found in younger Martian terrains. Sulfates like gypsum form in evaporating water in conditions where a body of water is slowly drying up and concentrating its dissolved minerals until they precipitate out of the water and form solid deposits. Finding sulfates on Mars is like finding the mineral record of a lake or sea that slowly dried out. A record written in chemistry, still readable billions of years later. But what happened to all that water? Where did it go? The answer involves the loss of something even more fundamental than water. It involves the loss of Mars's magnetic field. Early Mars had a global magnetic field, similar to Earth's. We know this because certain ancient rocks on Mars show evidence of having been magnetized when they formed, recorded the direction of the magnetic field that existed at the time, the way a compass needle records the direction of Earth's magnetic field. But the magnetic field of Mars weakened and eventually died out roughly 4 billion years ago. The interior of Mars cooled more rapidly than Earth's interior did. Mars is smaller than Earth, and a smaller object has more surface area relative to its volume, meaning it loses heat more rapidly. As the interior cooled, The convection in the liquid iron core that generates a magnetic field slowed and stopped. Without a magnetic field, Mars was exposed to the solar wind. The solar wind is a continuous stream of charged particles flowing outward from the sun at high speed. Earth's magnetic field deflects most of these particles, protecting our atmosphere from being gradually stripped away. Mars, with no magnetic field to protect it, could not do the same. The solar wind struck the upper Martian atmosphere and gradually eroded it. Atom by atom, molecule by molecule, the atmosphere was slowly stripped away over billions of years. As the atmosphere thinned, the greenhouse effect that had kept Mars warm weakened. Temperatures fell. Liquid water became impossible on the surface. The water that had flowed in rivers and pooled in lakes either froze underground or was lost to space, and the surface of Mars became the cold, dry desert it is today. This story is not just the story of Mars. It is a warning and a lesson. A magnetic field, which Earth takes for granted, and which humans rarely think about, is one of the key reasons our planet remains warm and wet and habitable. It is an invisible shield that has protected Earth's atmosphere for billions of years. Mars lost its shield, and it lost its water, and it lost its warmth. The geological record of Mars tells this story with extraordinary clarity. Now let us visit the places where the rovers are working right now. The places where human curiosity and human ingenuity meet Martian rock. Jezero Crater is a 49-kilometer wide impact crater in the northern hemisphere of Mars. It sits at the edge of the Isidis Planitia Basin, one of the largest impact basins on Mars. And what makes Jezero remarkable, what makes it the site of one of the most scientifically important rover missions in history, is what it used to be. Jezero is an ancient lake. Billions of years ago, a river flowed into Jezero Crater. You can still see where it entered. On the western edge of the crater, there is a delta, a fan-shaped deposit of sediment that built up at the point where the river slowed as it entered the standing water of the crater lake. This delta is one of the most well-preserved ancient river deltas on Mars. It is clearly visible in images from orbit. The layered sediment of the delta, laid down grain by grain over thousands or millions of years as the river carried material and deposited it at its mouth, looks remarkably like the deltas of rivers on Earth. Jezero Crater was chosen as the landing site for NASA's Perseverance rover because river deltas on Earth are among the most productive places to look for fossil evidence of ancient life. When a river flows into a standing body of water, it slows and drops the sediment it has been carrying. If that sediment includes organic material, including the remains of living organisms, that material can be buried and preserved for a very long time. Some of the oldest fossil evidence of life on Earth has been found in ancient river delta and lakebed sediments. Perseverance landed in Jezero Crater on February 18th, 2021. It has been driving across the crater floor and up into the ancient delta ever since, collecting samples of rock and sediment that scientists hope will contain clues about whether Mars was ever inhabited. The rover cannot determine this definitively on its own. Its instruments are powerful, but not capable of the kind of detailed analysis that could conclusively detect ancient life. Instead, Perseverance is collecting carefully selected rock core samples and sealing them in titanium tubes, leaving them on the surface in specific locations for a future mission to collect and bring back to Earth. When these samples arrive in laboratories on Earth, they will be analyzed with the most sophisticated instruments that scientists have, and it is possible, though far from certain, that those analyses might reveal something extraordinary. Microscopic fossils, chemical signatures of ancient biology, evidence that Mars was not always as lifeless as it appears today. We do not know yet. The samples have not come home, but the question is open, and Perseverance is doing the work of gathering the evidence that may one day answer it. As Perseverance drives across the floor of Jezero Crater, it photographs everything. It photographs rocks that have been abraded by wind for billions of years. It photographs the layered cliffs of the ancient delta, where each layer represents a distinct episode of sediment deposition. It photographs the rust-red soil and the pebbles, and the occasional larger boulder left behind by ancient floods. It uses its instruments to analyze the composition of rocks and soil, to look for minerals that formed in the presence of water, to measure the abundance of organic molecules. And it carries a small helicopter called Ingenuity. Ingenuity is the first powered aircraft ever to fly on another planet. It made its first flight on April 19th, 2021, a brief hop of about 40 seconds at an altitude of about 3 meters. That 40-second flight was a milestone comparable in its own way to the Wright brothers' first flight at Kitty Hawk in 1903. No powered aircraft had ever flown on Mars before. The thin Martian atmosphere makes flight extremely difficult, requiring rotor blades that spin much faster than helicopter rotors on Earth to generate enough lift. But Ingenuity proved it was possible, and it has since made dozens more flights, scouting terrain ahead of Perseverance and capturing aerial photographs of the Martian landscape from perspectives that no rover could ever achieve. In another part of Mars, in a crater called Gale Crater near the Martian equator, another rover has been working since 2012. Curiosity, the Curiosity rover, landed in Gale Crater on August 6, 2012, in a landing so technically ambitious that the engineers who designed it called it the 7 Minutes of Terror. The spacecraft carrying Curiosity had to decelerate from 21,000 kilometers per hour to 0 in about 7 minutes, using a heat shield, then a parachute, then rockets, and finally a device called a sky crane that lowered the rover on cables the last few meters to the surface. Every step in this sequence had to work perfectly. A failure at any point would have destroyed the rover. When confirmation arrived at Mission Control that Curiosity had landed safely, the room erupted in cheers and tears. Curiosity is the size of a small car. It is powered by a nuclear generator similar to those on the Voyager spacecraft. It has been driving across the floor of Gale Crater and up the slopes of a central mountain called Mount Sharp, or Olympus Mons, since it landed. Mount Sharp rises about 5.5 kilometers above the crater floor. Its slopes expose rock layers representing billions of years of Martian geological history. Each layer Curiosity drives through is like turning a page in a book of Martian history. Curiosity has made numerous discoveries of great importance. It confirmed that Gale Crater once contained a lake. The rocks of the crater floor contain minerals and textures that could only have formed in standing water. The lake in Gale Crater may have existed for millions of years. Curiosity detected complex organic molecules in Martian rocks, including a variety of carbon-containing compounds that are the building blocks of the chemistry of life. It measured the amount of radiation reaching the Martian surface, crucial information for planning future human missions. And it has found evidence that the chemistry of the ancient Gale Crater Lake would have been hospitable to certain types of microorganisms if they had existed there. Curiosity is still operating today, more than 12 years after landing. It has driven more than 30 kilometers across the Martian surface. It has drilled into rock in dozens of locations. It has sent back hundreds of thousands of images. It is a remarkable machine, built to last for 2 years and still going a decade later, slowly climbing Mount Sharp, still making discoveries, still telling the story of a world that was once very different. Let us now travel to the poles of Mars. Because the poles hold their own extraordinary stories, written in ice and dust. Mars has 2 polar ice caps, one at the North Pole and one at the South Pole. Both caps contain water ice and frozen carbon dioxide, dry ice. The relative amounts of each type of ice change with the Martian seasons. During winter, when the pole is in darkness for months, the temperature drops so low that carbon dioxide from the atmosphere freezes out and deposits as a layer of dry ice on top of the water ice cap. This seasonal carbon dioxide cap can extend a long way from the pole, covering a large fraction of the polar region in a thin layer of dry ice. During summer, when sunlight returns to the pole, the dry ice sublimates, turning directly from solid to gas and returning to the atmosphere. The water ice cap underneath, which has a much higher melting point, remains behind as a permanent cap. The North Polar cap is larger and contains more water ice than the South Polar cap. It is roughly 1,000 kilometers across and up to 3 kilometers thick. The total volume of water ice in the North Polar cap, if it were melted and spread evenly across the entire surface of Mars, would form a shallow global ocean roughly 5 meters deep. This is a significant amount of water. It tells us that Mars has not lost all of its water to space. Much of it is locked up in the polar caps and in permafrost beneath the surface. The ice in the polar caps is layered. The polar layered deposits, as scientists call them, are alternating layers of ice and dust, each layer representing a different period of Martian climate. As Mars's orbital parameters change slightly over long time periods, the climate of Mars oscillates, changing how much dust is deposited at the poles and how much ice accumulates. These orbital variations are similar to the Milankovitch cycles on Earth that drive our ice ages. The layers in the Martian polar deposits are a record of these climatic cycles, a climate record extending back millions of years, preserved in ice and dust at the poles of a cold red world. The polar caps are also the site of remarkable erosional features. In the South Polar region, during spring, when the dry ice cap sublimates from below as sunlight penetrates the translucent ice, the sublimating gas can burst upward through the ice, carrying dark dust with it and depositing it on the surface in spider-like patterns called areneiform terrain, or simply areneiforms, a word derived from the Latin for spider. These dark spider patterns, which can be hundreds of meters to kilometers across, are unique to Mars. They form fresh every spring and then disappear under new frost in the autumn. They are one of the most alien and beautiful features on the Martian surface, a geological process found nowhere else in the solar system. Now let us talk about the wind. Mars may have a thin atmosphere, but that atmosphere is not still. The wind on Mars is capable of moving the fine dust that covers the surface, lifting it into the air and creating dust devils and dust storms of remarkable scale. Dust devils are rotating columns of warm air that rise from the heated surface, picking up dust and spinning it upward into the air. They are common in the western United States and other desert regions on Earth, but on Mars they can be extraordinarily large. Martian dust devils can reach heights of several kilometers, far taller than any dust devil on Earth, though because the atmosphere is so thin, they carry much less material than an equivalently sized Earth dust devil. They leave behind dark tracks on the light-colored dust of the surface, winding tracks that curve with the wind, visible from orbit as dark sinuous lines on the pale Martian plains. These tracks can persist for months before new dust covers them, and their patterns tell scientists about the direction and behavior of the near-surface winds. Global dust storms are one of the most dramatic and disruptive phenomena on Mars. These are storms that can grow to envelop the entire planet, covering every surface and every feature in a shroud of suspended dust that can last for months. These global storms typically begin in the southern hemisphere during southern spring and summer. When Mars is near its closest point to the sun and the atmosphere is warming rapidly, a regional dust storm forms and begins lifting dust. If the conditions are right, the warm dust-laden air can create temperature gradients that drive stronger winds, which lift more dust, which creates stronger gradients, and a feedback cycle that can cause the storm to grow and spread until it has covered the entire planet. During a global dust storm, the sky on Mars turns from its usual butterscotch orange to a deep, dark brown. Sunlight at the surface can be reduced by as much as 99%, leaving the surface in a dim, hazy twilight even at midday. The solar panels on the Opportunity rover, which depended on sunlight for power, were reduced to almost nothing during major dust storms. And in 2018, a massive global dust storm covered all of Mars for months. The Opportunity rover, which had been operating for 15 years and was the longest-serving rover on Mars at that time, was unable to recharge its batteries in the darkness of the storm. When the storm finally cleared, Opportunity did not wake up. It had died in the darkness, its batteries drained, and its systems frozen in the cold. It was one of the most poignant endings in the history of space exploration. Let your breathing settle even deeper now. Feel the weight of your body, warm and comfortable. Let the sounds of the real world around you be distant and unimportant. Let yourself be here, very close to sleep, drifting through the quiet story of a red world far away. There are things happening on Mars right now that we cannot hear. There are marsquakes. In November 2018, NASA landed a spacecraft called InSight on the flat plains of Elysium Planitia on Mars. InSight was not a rover. It did not drive anywhere. It stayed in one place and listened. Its primary instrument was the most sensitive seismometer ever sent to another planet. A device so delicate that it could detect ground movements smaller than the width of a hydrogen atom. This instrument was designed to listen for seismic activity on Mars, for marsquakes, the way seismometers on Earth listen for earthquakes. What InSight found was that Mars is not geologically dead. Mars does experience marsquakes. They are not as frequent or as powerful as earthquakes on Earth, because Mars does not have active plate tectonics generating the constant geological activity that produces most earthquakes. But Mars does have seismic activity produced by the slow cooling and contracting of the planet's interior, by volcanic stress in the crust, and occasionally by meteor impacts. InSight detected hundreds of marsquakes over its 4 years of operation, ranging from tiny, barely detectable tremors to events strong enough to send seismic waves propagating through the entire planet. By analyzing the waves from these marsquakes, seismologists were able to do something remarkable. They were able to map the interior of Mars. Seismic waves travel at different speeds through different types of rock and liquid. By timing how long it takes seismic waves to travel from their source to the detector, and by studying how the waves change as they pass through different materials, scientists can determine the structure of the planet's interior. InSight revealed that Mars has a crust, a mantle, and a core, just as Earth does. The Martian crust is about 20 to 37 kilometers thick. The mantle extends to about 1,560 kilometers depth, and at the center, a liquid iron core with a radius of about 1,830 kilometers. This information is fundamental. It tells us how Mars formed, how it differentiated into layers, how it has cooled over billions of years, and why its magnetic field died. The size and composition of the core, and the fact that it is still liquid, help explain why Mars does not have a magnetic field today. The core cooled too quickly, and the convection that generates a magnetic field stopped. Without that magnetic field, Mars lost its atmosphere, and without its atmosphere, it lost its water and its warmth. InSight operated until December 2022, when its solar panels were finally too covered in dust to generate enough power to keep it running. Its last communication with Earth was a quiet goodbye, but the data it collected is still being analyzed, still yielding insights into the deep interior of a planet we have long watched from afar. Before we finish our journey tonight, let us look up from the Martian surface. Because Mars has 2 moons, 2 small, unusual moons that orbit close to the planet and tell their own interesting story. The larger of the 2 is Phobos. It is a small, irregular body, roughly 27 kilometers across at its longest dimension. It is not spherical, but rather potato-shaped, because it is not massive enough for its own gravity to pull it into a round shape. Phobos orbits Mars at an altitude of only about 6,000 kilometers above the surface. This is extremely close. Our own moon orbits Earth at an average distance of 384,000 kilometers. Phobos is so close to Mars that it completes an orbit in only about 7 hours and 39 minutes. This means that Phobos rises in the west and sets in the east, the opposite of every other astronomical body seen from the Martian surface, because it is orbiting faster than Mars rotates. It moves across the Martian sky so quickly that a person standing on the surface of Mars and watching Phobos would see it rise, cross most of the sky, and set again within about 4 hours. Phobos is also slowly falling toward Mars. Tidal forces are causing its orbit to gradually decay, In about 30 to 50 million years, Phobos will either crash into Mars or be torn apart by Mars's gravity and form a ring of debris around the planet, similar in some ways to Saturn's rings, though much less spectacular. The smaller moon, Deimos, is only about 15 kilometers across. It orbits at a much greater distance from Mars, about 23,460 kilometers, and takes about 30 hours to complete one orbit. Deimos appears in the Martian sky as a faint, star-like point of light, much smaller and dimmer in appearance than our moon appears from Earth. From the surface of Mars, Deimos is not much brighter than the planet Venus is seen from Earth. Both Phobos and Deimos are dark, heavily cratered bodies, and both are thought to be captured asteroids, objects from the asteroid belt that wandered close enough to Mars to be captured by its gravity long ago. Their dark color and composition are similar to certain types of carbonaceous asteroids. They are ancient, primitive bodies, remnants of the early solar system preserved in orbit around Mars. Phobos has one particularly dramatic feature, a crater called Stickney, about 9 kilometers across, which represents nearly a third of the diameter of the moon itself. The impact that created Stickney must have come very close to shattering Phobos entirely. Radiating from Stickney are long grooves and fractures that run across the surface of Phobos, scars from the enormous stress of that ancient impact. Phobos carries these scars like a face that remembers every difficulty it has weathered. The geological story of Mars is not finished. It is still being written. Every day, the Perseverance rover drives a few more meters across the floor of Jezero Crater. Every day, it photographs and analyzes and collects. Every week, it places another rock core sample into a titanium tube and leaves it on the surface, waiting for the mission that will someday collect these samples and bring them home. Every day, new images from orbiting spacecraft map the surface of Mars in finer detail, revealing new features, new geological structures, new clues to the ancient history of this world. Someday, human beings will stand on the surface of Mars. They will feel the thin, cold wind against their suits. They will look up at a butterscotch sky and see the sun, smaller than it appears from Earth, low on the horizon. They will look at the landscape of rust-red rocks and orange dust and feel the weight of 4.5 billion years of geological history around them. They will drive out to the rim of a crater and look down at layered walls of ancient rock that recorded the history of water and warmth and climate change. They will collect samples from places that cannot be reached by remote-controlled rovers. They will be geologists and explorers and pioneers reading the story of Mars in person with their own eyes, with a direct experience that no robotic mission can fully replicate. When that day comes, the rovers who came before them will be remembered. Curiosity, still slowly climbing Mount Sharp, Perseverance, driving across the Jezero Delta, Opportunity, silent in the dust where the storm caught it, Spirit, stuck in soft soil since 2009, still standing in Gusev Crater where it became immovable. These machines will be monuments, evidence of the first chapter of humanity's relationship with Mars, the chapter of exploration from afar, of learning from a distance, of building the knowledge that made the next chapter possible. You are very close to sleep now. Let your thoughts dissolve slowly, like dust settling after the wind has stopped. Let the images of Mars drift gently behind your closed eyes. The rust-red surface in the thin morning light, the vast and silent walls of Valles Marineris, the enormous rounded summit of Olympus Mons touching the edge of space, the ancient river delta in Jezero Crater, every grain of sediment a tiny record of water that once flowed freely on a warmer world, the polar ice cap catching the pale polar sunlight and glittering faintly in the long Martian day, the dust devils spinning lazily across the plains, leaving dark tracks that will last for months. All of this is real. All of this exists right now, tonight, while you drift toward sleep. Mars is turning on its axis at this very moment. Its sun is rising over some part of its surface right now. The Perseverance rover is parked for the Martian night, its instruments quiet, waiting for the dawn so it can drive again. The ancient canyon of Valles Marineris is dark under a sky full of stars, the same stars you see, but seen from a different angle, from 225 million kilometers away. The geological story of Mars is one of the most profound stories in the history of science. It is the story of a world that had every chance to become a second Earth, that had the water and the warmth and the chemistry, that went in a different direction, that lost its magnetic field and its atmosphere and its liquid water and became the beautiful, cold, quiet desert it is today. It is a story that makes us think carefully about our own world and what we take for granted. The thin layer of atmosphere we breathe, the magnetic field that protects it, the oceans that cover 70% of our surface, the living systems that regulate our climate, all of it more precious and more fragile than we usually remember. You are home on this pale blue dot with all of it, the water and the warmth and the air. And Mars is out there, waiting patiently, keeping its secrets in rock and ice and rust, slowly being read by the small machines we sent to ask the questions we most want answered. Sleep now, let everything be still, let your breathing be slow and gentle and even. You are warm, you are safe, you are exactly where you need to be. The dust on Mars is settling. The Martian night is cold and clear and full of stars. And you are here at the end of a long day, drifting down into the comfortable darkness of sleep. The geological story of Mars will still be there tomorrow. The ancient canyons will still hold their secrets. The volcano will still stand. The rover will still drive. And you will wake rested, and the world will be here, and everything will be all right. Sleep well. Good night.